started. So, let's see. Right, your homework is on the way. You're making some progress. I just remind you that the TAs do have their office hours on Thursday mornings before class, so I'm not sure how many people are making use of that, but they're there. I just also mentioned that I will not be here next week on Thursday, a week from Thursday. I'll remind you, we'll have a makeup lecture at some point. All right, so let's see where we're at and continue on. So we're talking about face-based representations, and we're particularly right now talking about the Wigner function. And the key idea is that we have a representation based on a operator basis that are labeled by points in face space, okay? So we have the important fact, the symmetric delta function, which forms a resolution of the identity. So given that resolution of the identity, we can think about representations of density matrices and other observables in the basis, so to speak, the operator basis on face space. And that gives us a representation, okay? Written in terms of the complex variables, which we will often do, our symmetric delta function is written as such, okay? Importantly, we also have the displacement operators, which are kind of the operator versions of plane waves, okay? So they have this form with this so-called symplectic inner product. We'll talk more about that in homework coming up. This is our face-based displacement operator that we've seen for a long time now. And the symmetric delta function is the Fourier transform of the displacement operator, the same way that delta functions are Fourier transforms of plane waves. So they're a Fourier dual. This is a Fourier transform on the complex plane, okay? And both the symmetric delta function and the displacement operators form an operator basis. So we can write as a superoperator, we can think about a resolution of the identity on the space of operators, okay? This is the operator vector space. The displacement operators and the symmetric delta functions form an operator basis. They form a resolution of the identity for operators as opposed to the space of Hilbert space in the states. Okay? So with that formalism, that gives us a way of expanding any operator in the appropriate basis. So given this resolution of identity, I can think about some operator on the Hilbert space and vectorize it. Think about it as a vector in the space of operators. Plug in this resolution of the identity, and this tells me that the operator is written as such. It is a integral over the face space weighted by some function, which is a representation, and we call this the Weyl symbol, okay? So it is the representation of the operator in face space.
That's how you spell it.
Weyl with a W, it's like Wolfgang. Or Wigner, right? Everyone clear on that so far? And in particular, the density operator like any operator, can be expanded in this way. And the Weil symbol with this particular normalization is called the Wigner function, okay? And it's because of this resolution of identity on Hilbert space, we have that this is normalized, okay? So a probability distribution over the phase space, if I integrate over the whole space, I get 1, okay? So this gives it the notion of a probability distribution, but it's a quasi-probability distribution. It's called a quasi-probability distribution because the Wigner function is real, but can be negative. So there's some notion of negative probability.
So all you're saying is that the Weil symbol for specifically the density operator is defined as rho W over pi.
Over pi.
Okay.
And it's defined that way so that it's normalized in
I
this
see.
way.
Based on another pi from the d squared. Right?
Oh, no,
Oh.
sorry, that should not be there. Pardon me, you're absolutely right.
I have a question.
Yeah.
So the density matrix given the subscript omega, that's
W, yeah.
sorry, W is being related to the Weil symbol, but how does it relate to A exactly?
No,
No.
A is just some arbitrary operator.
Okay.
For any operator, I can define the Weil symbol. Rho is an example of some operator. It has its own Weil symbol. The Wigner function is the Weil symbol divided by pi
Of the density.
of the density matrix.
So when we write t as a function of x and p, we're considering the Dirac delta function.
Yes.
And when we write the t as a function of alpha, do we go to the coherent state picture, or is that
No,
also
it's
a
just
Dirac
all what we've done here. So t as a function of alpha is equal to, so if I look at t as a function of x and p, I'm going to define alpha as this and a as this. Okay, so now I just plug in x is alpha plus alpha star over 2, etc., and I get the same. It's just with respect to the complex amplitudes. The other thing, the reason that there's that factor of 2 is different between them is because of this. And we discussed it in one of the lectures that you were in. All right, so that's where that's coming from. Very good. So importantly, in this formalism, we can look, for example, at the trace between, or can think about the inner product, this operator inner product between two operators that, as we said, we endow the operator space with an inner product that we inherit from the Hilbert space, and that inner product is the trace. And if I shove in a resolution of the identity over here, or I plug in, for example, this form of A over here, what I see is that this is equal to the integral over all space of the Weil symbol for A star times the Weil symbol of B. Right? So here I just shoved in a resolution of the identity. And this equals that. Everyone see that? So the inner product between the two operators which is the trace of that in this way, is the way we think about the inner product between functions, right? When we think about them, if we thought about the inner product between two functions, like two wave functions, it would look just like that. Okay, yeah.
So the super broad
Yes.
is a very, it's kind of a tricky, it's not just like it's a function, it's not like just a.
No, I would
It's not
say
more complicated.
it's no different than when we think about Kets of Hilbert space that we're familiar with in standard quantum mechanics. It's a label of a vector in a vector space. So operators or matrices themselves form a vector space. And I can just use our favorite Dirac notation as a way of dealing easily with how to do representations. The beauty of Dirac notation is the resolution of the identity. You never have to think. If you just use the resolution identity, you can shove it in wherever you like and get the representations. So really, this is just a label. I'm saying there is a vector in a vector space. Its representation by a function is through the fact that we have a set of basis vectors that are labeled by points on phase space. So for the inner product between the operator and the basis vector labeled by the point in phase space is the representation. In the same way that we think of this as the wave function, which is the representation of the state in the position space.
Is this similar to the idea of how people say that Pauli matrices can be used to represent any 2D matrix?
Yes, as people like us, we have said this. We used this last semester, and I remember it, but when we wrote down for any two-level system that it looked like a spin in a magnetic field, is because we were able to expand any Hamiltonian in the operator basis of the Pauli matrices, plus the identity. They form a resolution of the identity. In that case, a discrete set. This is a continuous set, but it's exactly the same idea. So, importantly, the expected value of some operator, let's say this is any old operator, I can think about this as the trace of rho times A. What I can think about, that's how I get the expected value. That is the inner product of rho with A. Rho is a Hermitian matrix, so the dagger is the same thing. And this, thus, is equal to, given this, the integral So again, I want us to look at this expression carefully. What I'm saying is that I can calculate the expected value of this observable by averaging, if you like, the operator over the phase space weighted by the Wigner function. It's the same way as I would say if I had some function of a random variable, if x is a random variable, and I have some probability distribution, classical probability distribution of x, and I wanted to know what is the expected value of some function of the random variable, how would I find it? I would weight by the probability distribution. Right? That's what we mean by the expected value. This is the same thing, but we're weighting it not by a probability distribution, but by a quasi-probability distribution. And that gives us the expected value of the operator.
Why do we have a 1 over pi?
The pi went here.
It's inside
So it's just the definition. The Wigner function is defined that way. we didn't have to do it, but it's just, we choose it that way so that it's normalized without the pi. Okay, so that's an important point. All right, so let's continue. Let's remind ourselves also by given this fact of the Fourier transform relationships that we had over there, we defined what we call the characteristic function, which is something that comes from probability theory. I will talk about at the end of class, I hope. The characteristic function chi is defined as 1 over pi times the trace of rho, not with t, but with the displacement operator. Okay? And this is the Fourier transform in the face plane of the Wigner function. Said another way, the Wigner function is the inverse Fourier transform of the characteristic function. So they're a Fourier transform pair on the plane. Okay? And the phase plane. So this is a way that we often use to calculate the Wigner function. What we often do, it's not the only way, we'll talk about other ways, is I calculate the characteristic function, because that's an easy thing often to do, and then take its inverse Fourier transform to find the Wigner function. Okay? You're doing that for homework now. So for example, one of the things we said at the end of class, we looked at the coherent state. In which case, my state is this. It's a pure state, let's say at alpha naught. And we found the characteristic function. The characteristic function for this problem, that's the expected value of the displacement operator evaluated at beta, that's the characteristic function. Right? And so, I'm going to get the factors right here. Oh, I'm bummed, I forgot my computer. Bummer. Maybe it'll work with the iPad, I don't know. I wanted to show you guys something, but let's see. Right. Right. So this is equal to 1 over pi e to the beta squared over 2 e to the alpha naught times star times beta minus alpha naught star alpha beta star. That's the characteristic function. The characteristic function is itself a Gaussian times a phase. This is a phase. And so when I take the inverse Fourier transform of this, what we find is that this is equal. So that is the Wigner function of a coherent state. As we discussed at the end of that, well, that is a Gaussian function. In fact, if I write this in terms of the real quadratures x and p, if I plug that in and normalize, this has a factor of 2, then what we find is that this is equal to 1 over pi e to the x minus x naught squared e to the minus p naught squared. Or it's equal to 1 over the square root of 2 pi delta x squared e to the minus x naught x minus x naught squared over 2 delta x squared times 1 over the square root of 2 pi delta p squared e to the minus p naught squared over 2 delta delta x squared equals delta p squared equals a half. Uh-huh.
Is the correct way to think about like the characteristic function is like it's a unit impulse because we said like the displacement operator was like equivalent to.
Sure, I think that's a way to think about it. That's helpful.
Okay.
I think really what the characteristic function is the Fourier transform of the Wigner
I see.
function. And it's called the characteristic function because it gives me the characteristics of a probability distribution, as we'll discuss in a little while. But I think it's really once you just think about it as the Fourier transform. Okay. But importantly, what we see here is what we expect. The coherent state, if I thought about the coherent state is a displaced vacuum state, right? And if we think about the vacuum state is a Gaussian in x and p. If we thought about the position or momentum representation, the wave function of the ground state of the harmonic oscillator, which is a vacuum, is a Gaussian. And this is just a displaced Gaussian that we think about if I were to try to draw. It's got some point here. Is some Gaussian in phase space. Peaked at some point that has some x naught and p naught with fluctuations that are the same as the vacuum fluctuations. Okay? Interestingly, this thing is everywhere positive. So in some sense that we'll talk more about, the coherent state is a kind of classical state. If we think about it from the point of view, it has a classical probability distribution of, if I were to measure the quadratures, x and p, there's a perfectly honest to God good classical statistical description of what I have in terms of classical probability, a joint probability distribution in both x and p. In fact, it's true for also if I had a squeeze state. If I had a squeeze state, what happens in the squeeze state is that I just have the squeezing here, that say we squeeze along R, I might have the x and p that are for the squeezed variables, where one of these guys would be a half times e to the 2r, say if it was squeezed along the x quadrature and anti-squeezed along the p quadrature. That as well would be a Gaussian function with a perfectly positive Wigner function. So in that sense, the squeeze state is classical. It's classical in a sense that is different from what we said in terms of its production from classical current, because there is no state producible from classical current that would be squeezed. But nonetheless, relative to this representation, it's perfectly classical. We'll come back to that thought in a moment. Yes, Tristan?
Are we defining classical here by the positivity or
Yes.
the Gaussian?
No, not good. Well, that's an interesting point. The answer is we are defining it by the fact that it's positive, which means that there is we define the system to be classical if there is a classical statistical description of measurement outcomes. If we have an everywhere positive Wigner function, then we have such a classical description. But the relationship to Gaussianity is interesting and important, which is to say that we have what we call Hudson's theorem. which says the only pure state with a Wigner function that is everywhere positive is Gaussian. That's to say, the only, if I have a Wigner function for a pure state that is everywhere positive, it must be Gaussian. If it's non-Gaussian, it must be negative. Okay, so there's a intimate relationship between positivity and Gaussianity for Wigner functions if they're pure states. I can have mixed states which are non-Gaussian, which are everywhere positive. But if it's a pure state and it's everywhere positive, it must be Gaussian. And the only states that are those are the squeeze states, of which a coherent state in the vacuum are examples, which is zero squeezing. So squeeze states are Gaussian states, and they are everywhere positive. Yeah.
So a squeezed state may or may not be squeezed, by definition?
Yeah, if it's got zero squeezing, it's still a squeeze state.
Okay, sure.
Sure. Yeah. It's just that R is, in that case, R is zero.
Okay.
Sure. I'll just call them squeeze states or coherent states.
I didn't mean to be today.
Yeah. Yeah. All right, let's look at another example. Let's look at a Fock state. Okay. So again, we can write down the characteristic function, which is the expected value of the displacement operator with this normalization. Okay? And this is a problem we did for homework. And the answer is e to the minus beta squared over 2 times the Laguerre polynomial evaluated at 4 times beta squared. Let me see if I got those numbers right. You remember that problem?
That was last semester.
Yep. And so it seems like a year ago. Right, and then I have to divide by pi. Okay, so I can take the inverse Fourier transform of that, and the answer I get is this. 2 times 1 over pi minus 1 to the n e to the minus 2 alpha squared times, oh, this one is not right. This is this, and this is this. Okay. When n is 0, this is the vacuum. It agrees with what we had over there. It's a Gaussian when n is 0, but when n is not 0, this is not a Gaussian, right? Because that's not a coherent state. In fact, if I look at it let's write it back in terms of the real quadratures. This is equal to minus 1 to the n over pi e to the minus x squared plus p squared, Laguerre polynomial evaluated at 2 times x squared plus p squared. Okay, that's the Wigner function. Now let's sketch it. Okay. So this Wigner function is a Gaussian that modulates a Laguerre polynomial. Okay. So you'll plot this for homework. If I look at the, let's look at the Wigner function. I'm going to just plot it. This is, as expected, this is rotationally symmetric. we expect that to be true. Why do we expect the Wigner function to be rotationally symmetric?
Because energy is uncertain. Or sorry, phase is uncertain.
Say again?
The phase is uncertain.
That's right, because this is a number eigenstate. The number eigenstate is an eigenstate of the rotation operator, right? Because the rotation operator is generated by the number operator. Remember, rotations in phase space we defined as this. This was the rotation operator. This is the number operator. This is an eigenstate of the rotation operator, therefore the Wigner function must be rotationally symmetric. Okay? So if I look at it as along the radius, though, let's look at this. I'm just looking at this on a cross section in that way. What we have is, well, if I look at this at the origin, this guy actually for L equals 1 is negative. And then it goes up, and then it comes over. And when this is on order 1, this is the peak. And at the origin, it's got a value of -1 over pi. So if I were to try to sketch this in the phase plane, what I have is the following. There is a ring which is concentrated around a radius of 1, which is what I expect if I thought about this from the point of view of having one quantum. This x squared plus p squared is the number operator. But in addition, it has a negative pole in the middle. Okay? Let me see if I can get this to work. If not, I might steal somebody's computer if they have it with them. If anyone has their computer with them, let's see if this works. Never done this before. This works.
Keep saying stuff.
Do. Yay! So this is the home page of our web for our class, but this is also the notes. So what are we looking at here? So these are plots of the Wigner function stolen from this paper. And what we see over here is the following. These are the Wigner functions as a function of, in this case, they're calling it Q and P rather than X and P, but position momentum. And the shadows are the marginals, right? There's what you get when you integrate over Q, it's the probability distribution of P, or if I marginalize and I integrate over P, I get the probability distribution of Q. This is a coherent state, and this is what we expect. The marginals are Gaussian functions. This is a squeeze state. The squeeze state, in this case, is squeezed along P and anti-squeezed along Q, but it, too, is a Gaussian state, which is everywhere positive. Interestingly, so this is what I was attempting to draw. This is the Wigner function for the first Fock state of the harmonic oscillator. This is the n=1 photon state, okay? As expected, it's rotationally symmetric around the origin, but it has this negativity. And it has to have that negativity if it's going to have the right marginals, right? Because what are the marginals? Okay. What are the marginals of, that is to say, what is the, if I have the first Fock state, which is the first excited state of the harmonic oscillator, what is the probability distribution in X and P? What's the wave function of the harmonic oscillator in the first excited state? It's a Hermite polynomial times a Gaussian, right? It's the first Hermite polynomial times a Gaussian. And that's what we see in these shadows. The you have a node, the first excited state has a node, and if it's going to be rotationally symmetric and have a node, it must be negative so that when I integrate it over that, I can cancel that and get something that is 0 somewhere. And similarly, if I project or I marginalize along P, I get the same wave function. So that's kind of cool. That's how that works. This is a problem you're looking at for homework, which is, suppose I have a quantum superposition of two coherent states, okay? Not a statistical mixture, but a superposition. That superposition, what we see here is two interesting features. One is each of the coherent states, this is kind of the Wigner function for each of the coherent states, but the fact that there is a coherent superposition between them means that there are interference fringes. And those interference fringes are shown here, which have this negativity in the middle. So this is sometimes called the Schrödinger cat state because we want to think about a macroscopic superposition of two different coherent states or two different positions or momenta. And so these are say the alive and dead cat, and these are the whiskers, as we call them, of the cat. Now, interestingly, again, this is kind of what we might expect if we thought about this from the point of view of what the marginals have to be. So if I had a superposition in position space of either the particle being in that wave packet or that wave packet, as if, say, I had a double slit experiment where the particle went through two slits. It could be here or it could be there, but it's in the superposition of those two. So this is the position space probability distribution. What is the momentum space probability distribution if I have a superposition of those? It's the Fourier transform, which is the diffraction pattern, the double slit interference pattern. And that's what you see. Well, you don't see it now, but you did. Come on, you can do it. Yes? Yes?
Would a statistical mixture by like intuition then be the same thing as D but without that middle part?
Exactly. Yeah, that's fantastic. And we're going to talk about that, how decoherence gets rid of these whiskers and leaves us with a superposition of the two. That's really a very important and very cool idea. So this negativity, preserving this negativity, is the sort of the heart of the quantum mechanics. But that negativity is the quantum aspect of this. Okay. So good. I hope you guys do that homework problem. Excellent. All right. Very good. I should mention the Wigner function, we said there is a method to calculate it, going through this route of first calculating the characteristic function and then taking its Fourier transform. That's what I just did. But there are other ways to calculate the Wigner function. Sometimes one of the other ways is more convenient than the other, okay? I'll just mention a couple. We'll talk about others soon. So one way is the way Wigner wrote it down originally, which you're deriving in homework. So the Wigner formula is the following. The Wigner function as a function of x and p is equal to the integral over a dummy variable psi star x minus 1 over 2 psi x plus y. So this is the way Wigner wrote it down originally. It's kind of interesting. I mean, firstly, it's clear that this gives the right marginal. If I integrate this over p, this becomes a delta function at y equals 0, and I get the square of the wave function. So it obviously marginalizes to the right thing when I marginalize over p. It also gives me the right thing if I marginalize over y. But this, what I see is that it's related somehow to the coherence of the wave function at two different points. How much coherence there is, and the Fourier transform is kind of an interesting way. Right? So this is another way you'll often see people talk about the Weil symbol. This is a general formula, not just for the density matrix, but I can write down the Weil symbol, because this is another way of writing the symmetric delta function in terms of this kind of outer product. Okay? There's another way of writing the symmetric delta function. It turns out that's shocking, which is, if I write the symmetric delta function as a function of the complex point in phase space alpha, this is actually equal to the following: twice the displaced parity operator. So pi here is the parity operator. Parity is the thing that takes x to minus x, or p to minus p, or is diagonal in the number basis, because the Fock states are eigenstates of parity with eigenvalue -1 to the n. These are all different representations of the parity operator, so often you will see people write the parity operator as minus the identity operator to the power n. It's an interesting way of writing the parity operator, but it is. It's just in the number basis. That's what it looks like. So it turns out that actually it's 2 over pi. This is a way of calculating the Wigner function if we can look at it from the point of view of, let me make sure I get all my factors right here. Okay, yes, no, that's not, this is not there. That's what I was getting confused. This is this. And this is thus equal to 2 over pi, because there's no 1 over pi here, the trace of the parity operator with the displaced. Right. Okay. So if I take the trace of rho with this divided by pi, I get that. Okay. So that's interesting. It's actually a way that we'll see in your next homework how we might measure the Wigner function. One way we might measure the Wigner function is to take the state we want to measure, displace it by some amount, and then once we've displaced the state, do a measurement of the parity. And if we look at the average parity, if we do that measurement many, many times, we get the Wigner function at that point. That's an example of what we call quantum tomography. Yeah?
If we can write the Wigner function in terms of, like, I want to say almost sweeping position space, could we also do a momentum space version?
Well, I mean, at the end of the day, we have to sweep over both position and momentum space.
I meant for the...
For this guy?
Yeah.
We could write this, there's an equivalent for a equivalent expression in terms of the momentum space wave function. We could equivalently write this if we Fourier transform the wave function. It would look very similar. We could do the same integral, but over a dummy variable in momentum space. Either would be fine. I just wanted to maybe emphasize one point, though, relative to this. What we see is up to a factor of 2. The symmetric delta function is a displaced version of the parity operator. That itself is a unitary transformation on this, right? And since the parity operator has both positive and negative eigenvalues, that tells us that the symmetric delta function is not a positive operator, because that's obvious now, because if pi is not a positive operator, a unitary transformation of it cannot make it a positive operator, which is one way to understand why the Wigner function can be negative. But we can also see from this that there's only so negative the Wigner function can be. There's a maximum amount of negativity because it depends what the most negative this can be. Since this can be at most -1 from this factor, what we see here is that the Wigner function is bounded between, can never be bigger than 2 pi and never less than -2/pi. That's the most negative it can be, and that follows from this. Because the parity operator can only be at maximum, have an expectation value of +1, and its minimum expectation value is -1. Very good. All right, so let's recap a little bit where we are. So far, we have seen 2 different phase-space representations. Starting last semester, we had the Glauber-Sudarshan P representation. And the way we defined it is we said, we're going to write the state as a statistical mixture of coherent states. And this defined a phase space representation. Okay? Question, what is the P representation of a coherent state? It's a delta function. It's a point where alpha equals alpha naught. So unlike the Wigner function, which was a Gaussian centered around this, this is a point. Right? And we had other examples like this. We showed that the thermal state was a Gaussian with having to do with the mean of the photons. The squeeze state for the P representation is highly singular. It's one of the things you're doing for homework, should you choose to do it. There is the P representation for a squeeze state doesn't exist. It's highly singular. And that is a fact that the squeeze state cannot be written as a statistical mixture of coherent states. It's got something which there is no classical current that can produce it. Okay? We've also now talked about the Wigner function. And that Wigner function was this. So we can write the state as a superposition of the symmetric delta functions weighted by the Wigner function. Okay? But there's other ways we could do it that we might say. Remember, we came to the Wigner function because we said that we had position representation, which said there was projectors on X and the probability distribution is just the square of the wave function, if it's a pure state. And we had momentum representation. I'll call it the mom representation because Benny likes it. And so the probability for finding that was the projector on that, and that gave us, which was the momentum. And we said we can't write down a similar representation x and b because there is no simultaneous eigenvector of both x and p. That, because x and p don't commute, they don't have a common set of elements. But we might think about a compromise. Suppose we, instead of thought about eigenstates of x and p, we thought about eigenstates of the annihilation operator. We know those exist. They're kind of the best compromise we have. That's something that's kind of like a simultaneous eigenvector of x and p. It's not really a simultaneous eigenvector of x and p. It's something that's an eigenstate of A in this compromise way. The coherent states are the eigenstates that are kind of eigenstatey of both x and p, kind of, right? So why not define a problem? So then I can think about this forms a resolution of the identity in the same way as x and p do. It has this factor of pi, but that's fine. And define then, this is a POVM. This is a resolution of the identity in terms of positive operators. I can think about a probability distribution relative to these projectors, normalize it this way, and define a probability distribution that I'm going to call Q, and this is for a pure state. So this is this, or equivalently 1 over pi, the square of that amplitude. So that is the overlap between the state and the coherent state. That is a honest-to-God probability distribution. This thing is known as the Q function. This is known as the Husini Q representation. Husini, Wigner, Glauber, they all did these separately, thinking about ways of thinking about quantum mechanics in phase space. This is a natural way to think about a probability distribution in phase space. And it's an honest-to-God probability distribution. Yes?
What's the difference with the P representation?
That's the P representation. The P of alpha does not equal that. If you take the, remember this is, let's call this a dummy variable. If I take the expectation value with alpha here, I'm not going to get a delta function. I'm going to get a Gaussian. So this is not what the P representation is. P representation is not the expected value. It's the thing that gives me the statistical mixture, but it's not that. The Q function is that. The Husini distribution is that. Okay? So we have these three representations, and what are they telling us? What is the interpretation of these different representations, and how are they related to one another? And is there a unifying theory that tells us how all these representations are related to one another? And the answer is, of course, yes. It was written down in a famous paper by one of our own faculty members when he was a PhD student, Kevin Cahill, who was Roy Glauber's PhD student, and that was his PhD thesis. And it's an amazing paper, everyone should read it. I'll give you the highlights. So, what this is all related to, so the challenge in writing phase-space representations is that X and P don't commute. Or equivalently, A and A dagger don't commute. So, whereas if we had only things that are a function of X or things that are a function of P, we could just replace the operator by its eigenvalue and get a representation. When you have operators where things don't commute, there's no clear way to do it because there's a question of operator ordering. So we can define representations relative to a particular operator ordering. Okay? So let me explain what I mean. Let's say I have some operator on our Fock space, our Hilbert space, which is some function of A and A dagger. Now, let's say I'm going to write this as a power series in A and A dagger, but when I write it in such a power series, there is a question of what order. Let me explain what I mean by that. So I'm going to say I can write this as a power series in powers of A dagger and A with some coefficients. I'll call these coefficients the normally ordered coefficients. Equivalently, I can write it in anti-normally ordered. Or in symmetric order. Let me explain what I mean by this, okay? So this is the same operator, but written in 3 different power series. These coefficients are not the same. Let's do an example. Let's say I look at the number operator. I can write the number operator like this, or I can write the number operator like that. Right? Because I can write it, I can just commute it. Or I can write it like that. These are the same operator, just I've written it in different operator orderings. In this case, the coefficients C and M are 0 except for when n equals 1 and n equals 1. Here they are equal to, when this guy is equal to 0, is a minus a half, and it's plus a half when n is 1. And in this case, in the antinormal ordered case, one of the coefficients here is minus 1 when n and m are 0, and the other coefficient 1. So there's 3 different ways I've written the same operator. Okay, it's the same operator, just written in different orders. However, they lead me to 3 different representations. Okay, so we're going to use this notation. We're going to have what are called S ordering, S ordered products, where we're going to call S equals 0 symmetric, for reasons that I'll say here. S equals plus 1 normal order, and S equals minus 1 anti-normal order. remember the normal order is where all the A daggers are on the left and all the A's are on the right. There's the anti-normal order is the opposite, all the A's on the left, all the A daggers. And the symmetric order is you look at all possible permutations and then you weight that, okay? So, with that, we're going to make the following definition. The S-ordered phase space representation. So given the operator, I'm going to call the S-ordered representation of that as the S-ordered power series where I set A equal to alpha and A dagger equal to alpha star. In other words, it is equal to the sum n and m go from 0 to infinity. These coefficients, S alpha star to the n alpha to the m. I want you to absorb that and think about this for a minute. This is a different function, even though all those operators were the same. These are not the same function.
These being coefficients.
That's saying this function, this whole, because the coefficients are different for the different ordering, this sum depends on S, okay? So this function is not the same function for normal order, symmetric order, and anti-normal order. Those operators are all equal, but these functions are all different. The operators were all the same because the A's and A daggers had certain commutation relations, but alpha and alpha star commute. You can just see that over here. If I looked at this, what this says is that the symmetrically ordered version of n is alpha star alpha, right? I just replaced it that. The anti-normally ordered, I'll call that n sub 0. N sub minus 1, the anti-normally ordered case, this is the normally ordered, sorry, plus 1. Anti-normal is what? It's alpha times alpha star minus 1, or alpha squared minus 1. This function is not equal to that function. And this function is different again. This function, the normally ordered, the symmetrically ordered version of n is alpha squared minus 1/2. These are three different representations of the number operator. We obtain them by writing the power series in a particular order, and then once we've chosen an order for where to put the A's and A daggers, we replaced the operators by numbers. And what we got is three different functions. These three operators are equal, but these are three different representations of the same operator. Okay? So, yes, ma'am.
So the equal sign in between these is sort of throwing me for a loop, because I understand why they're not the same operator, but you're sort of doing a different operation for each of these. You know?
But there are three different operators. This equals this.
Right.
This equals this.
Even though CA and CN.
That's right, because in this case, the coefficients were, in this case, C0, 0, and we had C11 for the normally ordered case is 1, and all the other coefficients are 0. In this case, the coefficients were C minus 1 is 1, and C00 was minus 1. They're a different set of coefficients.
But they lead to the same.
But this operator equals that operator, right? It's just when you write them in different orders, there are different coefficients in front of them. So this operator equals that operator. This power series equals that power series. However, when I replace the operators by numbers, I get three different functions. And the reason is because Whereas A and A dagger didn't commute, and the lack of commutativity is what gave me this. Once I put them in, these are three different functions.
I don't entirely see just like off the dome how you then go back from your A sub S of alpha back to your A hat.
Yeah, no, it's not easy. We're going there.
Okay.
Okay, now, so my claim now, so this is a way in principle to write down S-ordered phase space representations. We did it by hand for the case of the number operator because it was trivial. It was very easy for me to write down the three power series and then do the replacement. It was easy. But generally, God knows what those coefficients are. They're very hard to find. However, I claim the following is true, that the S-ordered representation of the operator is equal to the trace of the operator with the minus S-ordered delta function. I claim that this is the same thing as that. So T0 is the thing we've written down before. It's equal to pi, the symmetric delta function, the one we've been working with for the last few weeks. Psi, the plus one, is the normally ordered version. All the A daggers on the left times the delta function on the right. T minus 1 is the anti-normally guy. Okay. So the different S ordering, we're going to prove now that this is the case. That I can obtain the S-ordered representation, which is to say, write the power series and replace that's equivalent to this. Okay? We've already been talking about the symmetrically ordered delta function. That tell us that the symmetrically ordered power series is the Weyl symbol. This is the so-called S-ordered Weyl symbol. So let's show that, okay? To do that, we are going to use some trickeroonies, and we're going to look at our friend, the displacement operator. Okay. So the displacement operator, let's say, as a function of beta, is this. Okay. But if I write this as a power series, what this equals is the sum over nm, beta to the n minus beta to the m over n factorial m factorial times the symmetrically ordered we can see that because when we expand this in power series, we're going to get this to some power, and that's going to give us the symmetrically ordered. Okay? So this is getting close. We already see these are the coefficients in the symmetrically ordered power series of the displacement operator. The displacement operator automatically, we can see what those coefficients are. Yeah?
When you're writing that, you're just writing the anti-commutator, right? Like the curly brackets?
That's not an anti-commutator.
Oh, but it wouldn't be the same thing, like the symmetric. You have all of them on the left and all on the right, and then all on the right and all on the left.
I mean, if I look at, let's do an example. What's the symmetrically ordered version of this? Well, there are three different ways I can write this. I can write this as a squared a plus a dagger squared plus a dagger a. That's a symmetrically ordered. That's what that means. When I look at this to say that when I write the exponent in the power series, I'm going to get the exponent to some power. And that's going to be by the binomial expansion, all products. And that's the symmetrically ordered.
The one you wrote above for A, that should also be symmetrically ordered?
Everything is, that's what this is the symmetrical order. Or sometimes with the subscript 0. So we can think about the S-ordered product, where normal ordered, and when S equals +1, it's that. When S equals -1, it's that. When S equals 0, it's that. Okay? So, given this, I can see another trick. The other trick I can see is that if I remember the BCH theorem, I can write the exponent of this sum of operators as the product of these guys times the commutator, assuming the commutator itself is an operator that commutes with A and B. Okay? And that's true in this case. We've done this before. That tells me that the displacement operator is equal to e to the beta A dagger e to the minus beta star A e to the minus a half beta squared. But notice, this is the normally ordered version of this. This operator is what we call, there's all this notation. Remember the colon, we said there was a double dot where we ignored the commutator. So this guy is the norm. We can also write this as we do as D plus 1. It's the normally ordered version of this thing. So, and similarly, if I write it in the other order, just because what I call A and what I call B, the commutators in the other order. So, what we now have is the following. We can say the S-ordered D is equal to e to the S beta squared over 2 times D, right? Because I write it on the other order. When S equals +1, it's that, okay? So, given this, we have the following relations. That when we have the ordering that's not symmetric, then the operator D is orthogonal to the thing with the minus S. In other words, what I claim is that this is true. D with the S ordering is orthogonal to D with the opposite ordering. If they were symmetric, that's what we had, that was a delta function. But S with minus S cancels, right? Can you see that? If I plug in the S and minus S, that cancels in the exponent, right? So, what is true now is we have the following resolution of the identity. Before we had the displacement operators, when we started the lecture today, we said that the displacement operators form the resolution of the identity. Now we have this S and minus S. This, we'll pick this up next time, is the theory of what we call operator frames. The operator D sub S form a resolution of identity, but they are not orthogonal. They have a dual to one another. That's to say, the S and minus S orderings are dual to one another because this D sub S is orthogonal not to the thing with the same ordering, but with minus S ordering. Okay? There's going to be this duality, as we're going to see, between normal order and anti-normal order. Symmetric is self-dual to itself. Given this and this fact, we'll be able to find these coefficients and find the S-ordered representations. And what we will find in the end is the following. I'll just preview one last fact. The Wigner function is a symmetrically ordered representation. The Q function is the normally ordered representation. And the Glauber-Sudarshan Q representation is the anti-normal representation. These three representations represent three different operator orderings. Notice this duality. If I want to get the normally ordered representation of P, I have to trace it with the anti-normally ordered delta function because of this duality. And if I want to find the anti-normally ordered representation, I have to trace with the normally ordered delta function. There is this duality here. Okay. Now, I'll say one last thing. I'm a very stubborn person, as some of you may know. This is not often how the notation goes. Often people define the S-ordered. See, the way I've defined it is that the S-ordered guy is equal to the trace of rho with minus, right? Most textbooks define it the opposite way. They define the S-ordered representation as the trace with T sub S, not T sub minus S. Because they think, why carry around an extra minus sign? You have to remember the extra minus sign.
Oh wait, so but they're both positive on both sides.
Yes, people often define it with this being a plus sign. That's the way Glauber defined it. That's the way, not in Cahill. And it's in the textbooks often that way. I'm defining it this way. Why? Because that's what gives you this. With my notation, what you're looking at is the S-ordered power series. And to get the S-ordered power series, as we will see next time, you have to trace with the dual. Because, and that, it reminds you that there is this duality, as we'll see more, between the different orderings, okay? But, warning, almost everybody else defines it oppositely, okay? But this is, you're just, you're stuck with
So
me.
would it be like P if T was positive on there? Would it be
You know, so often they'll call this thing rho sub minus one.
So would that be considered the other representation?
It's the same representation, it's just how I'm labeling things.
Oh, so
I'm just labeling, I'm saying the S-ordered thing is what you get when you trace with t sub minus s.
I see.
But the way that in most textbooks they say the thing that you trace with plus s is what they'll say is the s-ordered representation. But I think that's backwards because it gives you the opposite power series. It doesn't give you the right power series. It doesn't give you the thing that I wrote down somewhere. Where is it? This. It doesn't give you this.
I see.
It gives you minus that. So I wanted to find the S-ordered representation as the S-ordered power series where you replace A with alpha and A dagger with alpha star. Yeah.
Does that mean if there does exist a fourth representation, there also has to be a fifth one to match pair?
That's right. So in principle, we could think analytically as S being a continuous parameter. Right now, we've defined S as having three different values, -1, +1, and 0. In principle, we can analytically continue because we have this definition and think about S as just a continuous parameter. But there's always this duality between S and -S. The only one that's not dual is S equals 0. Then it's self-dual to itself. Yeah.
So the Q function is always positive, right?
Correct. It is correct. So we'll talk more about this next time, but we've got to get to the let's cut. I'll take your questions outside. We'll continue.
Could that be complex?
Well, we can think about all those things and what